Welcome back to Solids and Liquids in Part 4, which is the final section of this unit. We're going to be talking about semiconductors and alloys. Let's get started. First of all, let's look at types of conductors. So if you have a good conductor, then there is the valence band, that is where the valence electrons are, and the conduction band. The electrons can freely move up into the conduction band, and then if they can move there, the electrons can freely move wherever they want to, all around, and then we can conduct electricity because electrons are moving. If you were to have an insulator, that is, it doesn't conduct electricity, there's a huge energy gap in between the valence electrons and where the electrons would need to be if they were going to conduct electricity in order to move. So the electrons have a hard time jumping between there. Nope, can't do it. And so it insulates or does not conduct electricity. Well, this time we're going to be talking about semiconductors, so that there's a really small energy gap in between the valence band and the conduction band, and electrons can move up to the conduction band to move around, but it's not really easy, so they also can not, and so they're going to kind of go somewhere in between. So a semiconductor conducts electricity somewhat, but just not very well. For example, silicon is a good type of semiconductor. So semiconductor conductivity between a conductor and an insulator because there's a small gap between the filled and unfilled orbitals, so electrons can jump. From valence shell to the conduction band. So you'll typically see semiconductors among the metalloids, such as silicon or carbon. And these things are semiconductors. They have a really small amount of energy in between where the valence electrons are and the outer orbitals. And they also each have 4 electrons that it contributes, and then 4 electrons that come from another silicon. So every silicon can contribute 4 electrons. And that's kind of what makes it so good. Let's see if I can do this. Whoa! So every silicon can contribute 4 electrons, and then there's 4 shared electrons, and those electrons can jump up and move as they wish. There are 2 types of semiconductors that we're going to be focusing more on, and those are N-type semiconductors and P-type semiconductors. These are both types of doped semiconductors. A doped semiconductor is something that has a mixture of elements. Used to increase conductivity. So in an N-type, the N stands for negative. To make the silicon negative, you would use an atom that has an extra electron, and since electrons are negative, that is a negative semiconductor. So let's just say we had here a phosphorus. This is a phosphorus nucleus, so a big, oh, can't read that. Let's try again. A big P for phosphorus. So phosphorus has 5 valence electrons, so it had its 4, the same as the silicon did, but then it also has 1 more because it's a phosphorus. And that extra electron can easily move up into the conduction band and can kind of float around and conduct electricity, because that extra electron can go wherever it feels like going. If you were to have a P-type semiconductor, P stands for positive. So you would dope the silicon with something that had 1 fewer electrons, so only 3. This boron has 3 electrons, and it leaves a hole where an electron should go, so any of the other silicons can cause their electrons to go and fill in the hole, so then another electron can go fill in where that electron left, and then another electron can go fill in where that electron left, and you end up conducting electricity. So either way you can conduct electricity. So an N-type semiconductor has elements in the material replaced by atoms that have extra valence electrons. Replace an atom with another, that has an extra electron. And for p-type, you're going to replace an atom with another that has one fewer electron. Well, then you could put a p-type and an n-type together to create a p-n junction. So in the p-type, remember that we have a bunch of holes because you have atoms that have not quite enough electrons. And so those holes then are positive because they're not filled with electrons. And then you have an n-type, and let's say you put the n-type next to the p-type, and the n-type has a whole bunch of extra electrons, so a bunch of extra negatives. Well, what you can see is that some of the negative electrons might jump in to fill in some of the holes that are created by the p-type, and then you'll get some negatives on this side and some positives on this side. So overall, the n-type will have a net positive charge, and the p-type will have a net negative charge. And then you've got a p-n junction, and now you have electricity conducting. From the n-type to the p-type, the electrons can just jump across. Well, what if you put a battery into it? Would that make it work any better or worse? And it all just kind of depends on which way you face the battery. So let's use this little physics terminology. That thing right there is a battery. And this side of the battery is the positive side, big plus. This side of the battery over here is going to be the negative side, big minus. Alright, so if you have the positive side of the battery on the left, and then the n-type has a whole bunch of negative electrons, those negative electrons are going to be attracted to the positive side of the battery. And so you have the negative side of the battery on the right, so the holes, or all of the electrons, are going to fill in so that the positives are on the left and not on the right. Which means you don't have electricity conducting, because the electrons aren't trying to go to fill in the holes. All the electrons are going away and not completing the circuit. No electricity. Because there's no electrons jumping the gap between the p and n type. But if you take that same battery, the same battery as we had before, but this time you reverse it, so you have the negative on the right and the positive on the left. So now the electrons, let me draw this in a different color, the electrons that were over on the left are going to run to the right because that's where the positive charge is. And the holes that were on the right are essentially going to run to the left because that's where the positive charge is. And as long as the battery is connected, it will move and move and move, and the electrons will go, and the electrons will go, and the holes will move, and everything keeps moving and moving and moving. And so then you have electricity. And so a diode works by switching back and forth which way, whether the electricity is on or whether the electricity is off, which way the battery is facing, and you can get a semiconductor and a computer chip that works really, really well by switching on and off the electricity in that way. Next we have types of alloys, and this is our very last section for this unit. So an alloy is a mixture of metals. An alloy will typically retain its sea of electrons, so it is generally still conductors. And there are two types of alloys that the College Board wants you to know about. One of them is a substitutional or substitution alloy, and the other is an interstitial alloy. So we'll talk about substitutional first. The host metal is replaced by another of a similar size. The host metal is replaced by another of a similar size. The density typically lies between the component metals. The alloy remains ductile and malleable. So the solvent metal atom, or the one that we had before, let's say we're trying to make some gold mixture. So these are all gold atoms. That's a gold and that's a gold. But we want to make the gold a little bit stronger, so we're going to put some, I don't even know what's stronger, platinum in it, or lead in it, or copper. And so then these are little platinum atoms that are approximately the same size, and they just kind of substitute, not a gold, a platinum. They just kind of substitute and fill in. And since it just substitutes, the ductility remains the same, the malleability remains the same, it tends to have the same approximate properties. The other thing you can do is an interstitial alloy. And interstitial means in the holes. So the host metal is replaced by another of a much smaller size that can fit in the holes between the atoms. The interstitial atoms do not appreciably expand the metal, so the density is often substantially increased. The interstitial atoms will make the lattice more rigid, decreasing the malleability and ductility, which is probably what you're actually going to want to do with gold, to make the gold not so soft, to make it a better thing for jewelry. So our solvent metal atom, again, let's pretend like this is gold. And we're going to put in something that's much, much smaller, let's say this time copper. And so this copper is so small, it just fits in between all the little holes. And so that's going to make the gold stronger because it's there's more densely or more tightly packed. And those are the two types of alloys you need to know, and that's all you need to know about semiconductors and alloys. So I hope you had a good time learning. Bye!